Play a few seconds of video for a modern AI model, and something quietly remarkable happens. It does not just read a caption someone typed underneath. It takes in the actual picture, frame by frame, and it takes in the actual sound at the same time. One model, watching and listening to the raw material. The question is how? How does a machine that only ever deals in numbers turn moving pictures and human speech into something it can think about? That is what we are going to build, piece by piece. Start with a single frame. To you, it is an image. To the model, it is a grid of pixels, and every pixel is just 3 numbers, the amount of red, green, and blue. A normal high-definition frame is about 2 million pixels, which is roughly 6 million numbers. The model never sees a cat, or a face, or a ball. It sees this wall of numbers, and everything it understands has to be squeezed out of that. You cannot hand 6 million numbers to the model one at a time and hope for the best, so it does something clever, borrowed from a design called the Vision Transformer. It lays a grid over the frame and cuts it into small squares called patches, often 16 pixels by 16. Instead of millions of loose pixels, you now have a tidy tiling of little tiles. Then each patch gets flattened and passed through a small layer that turns it into a single short list of numbers, a vector. That vector is a token, one patch in, one token out. A frame that was a couple hundred pixels on a side becomes a couple hundred tokens. And here is the trick that makes everything else work. A token from a patch has the same shape as a token from a word. So a frame is no longer a picture. It is a short sequence of tokens, each one carrying a tag that says where in the grid it came from. And a sequence of tokens is exactly what a transformer already knows how to read. We have quietly turned seeing into reading. Now bring in time, and things get heavy fast. A video is not one frame, it is many. If a single frame is 200 tokens and you sample even one frame per second, then 1 minute of video is 12,000 tokens. A few minutes is hundreds of thousands. This is the single biggest reason long video is hard for AI. The tokens explode, and the cost of paying attention to all of them grows even faster. To make sense of that river, the model uses attention. Every token is allowed to look at every other token and decide what matters. Inside one frame, that ties the ball to the foot that is kicking it. Across frames, it tracks that same ball moving through the air. This attention across time is how a stack of frozen stills becomes motion, and how the model starts to grasp that one thing caused another. Now the other half of the video, the sound. Audio starts as a waveform, and a waveform is brutal to feed in raw. Sampled 16,000 times a second, a short clip is a fire hose of numbers, with no obvious structure. So we do the same kind of move we did with the picture. We change what the sound looks like before we hand it over. We turn the sound into a picture. Using a standard transform, the waveform becomes a spectrogram, a two-dimensional image with time going one way and frequency going the other, bright where that frequency is loud. Then we warp the frequencies onto the Mel scale, which spaces them the way human ears actually hear. Now the sound is literally a picture, and we already know how to handle pictures. From there, it is the same recipe. Chop the spectrogram into short slices, around 1/10 of a second each. For each slice, snap its energy into one of a fixed set of bins, like picking the closest entry from a small vocabulary of sounds. Each slice becomes a discrete token, speech, music, a door slamming. All of it is now a sequence of tokens, just like words. And this is where it all comes together. Text tokens, video patch tokens, and audio tokens are all projected into the same shared space and braided into one single stream. A picture of a mouth, the sound of a voice, and the written word for what was said now sit right next to each other in the same river, and one transformer reads the whole thing at once. There are 2 ways to arrive here, and the difference is the whole story. The older way is bolt-on. You take a language model that only ever learned text, and you staple a separate, pre-trained vision system onto the side with a small adapter. It works, but the 2 halves grew up apart, and sound is often a third piece bolted on after that. The other way is native. Pixels and audio are tokenized and fed into the same model in the same space from the very start of training. One brain learns text, sight, and sound together, not a reader that learned to squint at images, one stream where a frame, a spoken word, and a typed word are all just tokens. That native approach is exactly what Thinking Machines Lab put into Inkling, released in the summer of 2026. It is a large mixture of experts model, 975 billion parameters in total, but only about 41 billion active on any given token, so it stays affordable to run. Images and video go in through a hierarchical patch encoder. Audio goes in as a discretized Mel spectrogram. the picture of sound trick we just built. It takes text, images, and audio in and writes text out. And crucially, the weights are open, released for anyone to download and fine-tune. Remember the token explosion? To reason over minutes of video and speech, you need somewhere to put all those tokens, and Inkling gives itself a context window of up to 1 million of them. That is what a native, single-stream design really buys you. When a character on screen starts to talk, the model does not consult a vision module and then an audio module and try to reconcile them. The mouth and the voice are already sitting side by side in one river of tokens, and attention can simply connect them. That is how a machine made of numbers learns to watch and to listen at the same time.